This is my video number 13, right, on linear system with a constant coefficient. We still deal with that x dot equal to ax plus by and y dot equal to cx plus dy, where the roots, are given as that a plus d plus minus square root a minus d squared plus 4bc. Okay, we have done two cases. We have real distinct roots and we have imaginary roots, complex roots. Now we deal with a repeating roots. We have case number 3, okay, where lambda 1, to have a repeating root, we have this part must be 0. Okay, this part must be 0, so what left is only a plus d over 2. So our root is lambda 1 is equal to lambda 2 equal to a plus d over 2, where this is obtained by setting, or if we have a minus d squared plus 4bc, this is 0. Okay, so we call it as a double root or repeating root. So if we take so if we let lambda 1 lambda 2 equal to u, so which means we have our u is equal to a plus d over 2, and this is for the case this can happen as ad minus bc. This is different than 0. Okay, now for the special case, let's say for the case A, we have when b equal to c equal to 0, in this equation. Let's call this equation number 1 for this video. Okay, let's say b equal to c equal to 0, then our system becomes we have x dot equal to ux plus y dot equal to uy. So if you remember this part here, this is when we deal with the first case. We do the transformation, and our transformation becomes x dot equal to lambda 1x, y dot equal to lambda 2x. Now in this case, since lambda 1 equal to lambda 2 equal to u, so I just put the u there. So we have x dot equal to ux and y dot equal to uy. And the solution for that system, is given in the form x equal to c1e ut and y is equal to c2e ut. Okay, so from there we have this x c1 ut and cy. You can of course substitute this ut into that, so this is ut is equal to x over c1. You can write here eut is equal to x over c1, then you can substitute into that, so you have y equal to c2 over c1 x. So this is just a straight line. This is just a straight line. So this is your trajectories, and that's your trajectory. So which means you have your trajectory becomes is a straight line So a straight line. So we have just that. Okay. Now, just a straight line passing through not, yeah, passing through not. So in this case, we say not or 0 is called proper knot. And it is asymptotically stable. Yeah, asymptotically stable. If A plus D negative, and unstable if A plus D positive. So when A plus D negative, yeah, so we have this knot. So this knot will, as t goes to infinity, so the point approaching the critical point not. So that's why this is become asymptotically stable. Whereas when A plus D positive, we have I just put that, you can write more. We have the direction away from the critical point. So that's why it's become unstable. Alright, so this is the first sub case when for the case 3. Yeah, for the case 3. So remember that for the case 3 we have a repeating root, and special case when b c equal to 0. So we have that. Okay, our system reduced to that, where the solution look like that, and our trajectories becomes that. So this is just a straight line. Okay. Now we have for the second case. For the second case, I put it B here. Yeah, for the second case, we may assume, yeah, for the case, or assume B is different than 0, then the transformation zeta equal to A minus D over 2B x plus y, and eta equal to 1 over b x, transform our system, which is system 1, into, we have zeta dot equal to A plus D over 2 zeta, and eta dot equal to epsilon plus A plus D over 2 eta. Okay, so for this reason we consider, so therefore we consider the system x dot equal to ux. Yeah, we have x dot equal to ux, you consider that as u, as discussed, and then y dot is equal to, we have x plus uy. Okay, so with that, by considering that system, okay, we have the solution given. So the solution for this system, yeah, solution for that system is x equal to c1e ut and y equal to c1t plus c2e ut. So if C1 is 0, yeah, if C1 is 0, that one is 0. So what we have, the rectilinear trajectory in the y-axis. Yeah, we have 0, so we have rectilinear trajectory in the y-axis. Yeah, I can write here, if C1 is 0, so we have the rectilinear trajectory is the y-axis. The y-axis. And otherwise the trajectory are asymptotic in the y-axis, since y over x becomes infinity. So you can see that as y over x, y over x goes to infinity as t goes to infinity. Of course, you can check those things. Yeah. So in this case, we call the critical point. So the critical point 0, 0 is called, critical point 0, 0 is called, critical point 0, 0 is called knot or improper knot. We say improper knot. It is asymptotically stable, asymptotically stable if A plus D negative, and unstable if A plus D positive. So the trajectories or the phase portrait look like so this is for the asymptotically stable case. Here we have that okay. So this is asymptotically stable case. For the unstable, you just change the direction. For the unstable, you just change the direction. So for the example, I give two examples for this case. Example. Consider the system x equal to negative 2b x dot equal to negative 2x and y dot equal to negative 2y, and another system b, we have x dot equal to ax minus y and y dot equal to 4x plus 4y. And for this, you can check this. For this case, you have a stable proper knot, and for this case, unstable knots, improper knot. In this case, this is improper knot and unstable. So please check this. Check this. Check. Okay, now let me wrap up the in general, we have a theorem. The proof is given during our lectures. So the system x dot equal to ax plus by and y dot equal to cx plus dy with AD minus BC, this is not 0, where A, B, C are real, where A, B, C, D are real, then 0, 0 is an isolated critical point. I have defined what is isolated critical point. Isolated critical point, and we have stable if, so those critical point is stable if the root, the roots of the characteristic polynomial, CP, characteristic polynomial, are purely imaginary, and number 2, we have asymptotically stable. If the roots have negative real parts, and we have 3, we have unstable if the root have positive real parts. The roots have positive real part. Okay, so I think that's for the linear system with constant coefficient. We have covered 3 cases, different cases. We have stable, we have asymptotically stable, we have unstable with various type of trajectories. We have proper node and improper node. So we have spiral, we have a family of circle, and so on and so forth. So if you don't mind, let me give you some exercise. Let me check just a minute. I think I have some exercise for you to consider. If you have a time, you can do. If you don't want to do, it's okay. Let's say x dot exercise. Some exercise for you. One, let's say x dot equal to 2x and y dot equal to 3y. I think I do want to write this. I just put it here. Okay, just copy this one. Oh, I think you can see that. Can you? Just a minute. That. Okay. So we have x dot equal to 2x, y dot equal to 3y, and that's number 2. Number 1, number 2, you have x dot equal to minus x minus 2y, y dot equal to 4x minus 5y, and so on and so forth. So we have how many there? 7 exercises for you to do. Try to do this exercise. Of course, there is some more complicated exercise. You can see in any a differential book here. Elementary differential book is fine. Okay, so I think that's all for now. Thank you.